So the next speaker is Irene Gaussarian. She did a lot of work on semantic of programming languages, and she will present a joint work with Andrei Arnold and Patrick Kadelsky. Thank you, Irene. Go ahead.
Thank you, Alex. Thanks for inviting us. We are very happy to present our work in honor of Boris, who was a wonderful person. So this talk will consist of two parts. First, we recall what congruences.
Sorry, can you also adjust the camera? You only see your glasses.
Okay, is it better? And the first part, congruences, congruence preservation, the known notions. And the second part, the contributions of the present work. So now for the first part, a congruence on a binary algebra A with a single binary operation star is an equivalence relation, which we call sim on A, which is compatible with the operation. Namely, if A is equivalent to A prime and B equivalent to B prime, then A star B is equivalent to A prime star B prime. Now for congruence preserving function. A function is congruence preserving if and only if for any congruence on A, for any two n tuples of x's and y's, which are pairwise equivalent, their images by f of x1, xn, and f of y1, yn are also equivalent. So which functions are congruence preserving? The most basic example is polynomial functions. A polynomial on the variables x1, xn is a term with which is defined with constants and x1, xn. More formally, is the least set containing A union x1, xn, which is closed by the operation star. So polynomial functions are CP, but not all CP functions are polynomials. We'll see that right now. From now on, CP means congruence preserving. So for instance, the following function, or g of x, which is here, on a very simple binary algebra, which is a positive integers with addition. This is a Bessel-like function. It's congruence preserving, but it's not polynomial because its power series expansion is infinite. So an algebra is said to be affine complete if this converse is true, namely if every CP function is polynomial. And we have just seen an example, n positive integers with addition, which is not affine complete. This implies that the Fremanoid with one generator, A star and concatenation, is not affine complete either because it's isomorphic to n with addition. So affine completeness has been very well studied in, well, very well, reasonably well studied in commutative algebras. For instance, there is a complete characterization of abelian affine complete groups. But it was not studied in non-commutative algebras, neither in non-associative algebras. So we decided to study affine completeness in non-commutative algebras, and we took as example the Fremanoid generated by an alphabet of generators, sigma with concatenation. And we proved that as soon as the Fremanoid has at least 3 generators, a function is CP if and only if it is of this form, namely x gives W0, x, W1, etc., x, WK, where W0, etc., WK are words in the Fremanoid. Hence, the Fremanoid with at least 3 generators is affine complete. I've stated here the theorem for a unary function f, the theorem for an arbitrary arity function f, for an n-ary function, is the same, except that it's heavier to state, so I won't state it. So to summarize, the Fremanoid is not affine complete if it has just one generator, and it is affine complete if it has at least 3 generators. What happens if it has exactly 2 generators? Well, this is the object of our present work. Let me, before speaking of the Fremanoids, talk about another monoid, which is also free, the algebra of binary trees with labeled leaves. So I must say that these are not exactly the trees which were considered by Bruno Courcelle. My trees are binary, and they have 2 variants. One, the complete trees, each, and they are finite. The complete trees, each node has 2 successors or 0 successors. And the leaves are labeled by elements of sigma, not the nodes, internal nodes are not labeled. And the non-complete trees, nodes have either 2 successors here, 1 successor here, or 0 successor, the leaves. And the operation on the binary operation in both cases consists of gluing 2 trees together by adding root. For instance, I would add root here and an edge, and I would glue these 2 trees together. So the results of our present work are the following. The algebra of trees, binary trees with labeled leaves, are affine complete as soon as the alphabet of labels has at least 1 element. Second, the problem we started with originally, the algebra of words with concatenation is affine complete as soon as it has at least 2 generators. The proofs are very similar. They are by induction on the arity of f. The case n equals 0, the function f is a constant. It has no argument. It's obvious. A constant is a polynomial. Okay, so we will sketch the proof for the Fremanoid for the case n equals 1 for functions of arity 1. And going from n to n plus 1, well, it's the same except that it's heavier. So we will use only some special magic congruences. And from now on, f is a unary CP function on the alphabet sigma, on the monoid sigma star generated by the alphabet A, B star. Oh, and I forgot to say something that we had previously proved that the monoid, where is that? With Fremanoid with 3 generators was affine complete. Well, the method for 3 generators does not work at all for 2 generators. We took us a long time of work and a lot of work to adjust, to find a new method, completely new method, to get it to work for free algebra with 2 generators. So let me go back to my proof. The congruences we will use are only some special congruences, which I could call magic. I'll tell you why later. First, let me, before giving the proof idea for unary f on the alphabet, on the Fremanoid generated by A and B. So what we want to prove is the converse, namely that if f is CP, it's polynomial. So there exists k, w0, wk, such that f of x is of this form. I defined an auxiliary result. Let me first define the length of a word u in the Fremanoid, u between 2 bars, to be the number of occurrences of letters in U. For instance, the length of A, X, B, X, A is 5 because there are 5 occurrences of letters. If P is a polynomial, it has a degree. The degree is the number of x's in P of x. For instance, if P of x is AX, B, X, A, the degree of P of x is 2 because there are 2 x's, one here and one here. And the length of P of U is the length of AU, BU, A. It's twice the length of U plus 3. So the length of P of U is an affine function of U. So if f is a function Cp who pretends to be a polynomial, it better has to behave, namely, the length of f of U should be an affine function of U, of the length of U, like for polynomials. Well, it does work. Let us define U, sim V, the equivalence U and V have the same length. This is a congruence, and with the help of this congruence, we can prove that if f from the Fremanoid into itself is Cp, then it has a degree such that the length of f of U is equal to k times length of U plus the length of f of epsilon. Epsilon is the empty word. Exactly the same situation as with polynomials. Let us start with the simplest possible congruences on sigma star. We take two words U and V. UV, sim UV is a congruence generated by U is equivalent UV to V. In order to be able to do something with that congruence, we will suppose that the length of U is larger than the length of V in order to be able to reduce words. So a word W is UV reducible if and only if U occurs in W. And then we reduct it, we reduct W by replacing U by V as much as possible to obtain the shortest possible word equivalent to W. But it's not so easy. Let's take an example. If U is AA and V is B, so we do have a length of U larger than length of B, length of V, let us try to reduce shortest possible equivalent to AAA. Either we reduce the first two A's and we get BA, or we reduce the last two A's and you get AB. So we get two shortest equivalent words to AAA. The reduct is non-unique. This is because U self-overlaps in W. So we have these first two, which are a U, and these last two, which are also a U. So this must be avoided. And here is where our magic comes in. We had to find a set of words, tau in T, which will never self-overlap. And these T are the words of the form AN, BA, BN, n strictly larger than 1. And these words were found by André Arnaud. And we still have length of V less than length of tau. Now, each congruence class has a unique canonical shortest representative. And we have a nice result that U is equivalent tau V to U prime, if and only if they have the same reduct. They both reduce in the single word W. So with magic, we have each U has a very unique decomposition of the form U0, tau, U1, tau, etc., tau, UM. We exhibit the occurrences of tau in U to be able to reduce them later on. And each of the UIs is tau irreducible. We apply this to U equals f of tau. And then what shall we do? We will reduce via the equivalence steam tau V, tau x, tau x. Basically, we replace taus here by x's, and the UIs are tau irreducible, so they won't move. This is a polynomial, a nice, good polynomial, and we'll see that magic will help us with this polynomial. First, we show only partial polynomiality of CP function, namely CP function is polynomial, but only on some set of arguments. The polynomial p tau, which we just defined, ret tau x of f of tau, satisfies p tau of tau equals f of tau. This was by definition. The degree of p tau is less than the degree of f. This is easy to be seen. And for all v such that the length of f of v is less than the length of tau, f of v is ret tau v of p tau of v. This is easy to prove. If the length of v, f of v, sorry, is less than the length of tau, then f of v is necessarily irreducible, tau irreducible, because it's shorter than tau. Hence, f of v is its reduct modulo tau v. So f of v is equal to ret tau v. So these two words here reduce into the same word f of v. Because f is congruence preserving, of course, and these two are equivalent. Similarly, p tau is a polynomial, so it's congruence preserving. So p tau of tau and p tau of v are congruent. Hence, they have the same reduct, which is ret tau v of p tau of v. But f of tau is equal to p tau of tau. So these two are equal also. So please remember this lemma p tau, because I will use it later. Lemma p tau tells us that on all v's such that f of v is less than tau, f of v is ret tau v of p tau of v. Now, we are not completely happy because f of v is not exactly equal to p tau. It's equal to some reduct of some p tau. So we'll try to do a little bit better. If, moreover, the degree of p tau happens to be equal to the degree of f, then for any v with f of v less than, shorter than tau, f of v is equal to p tau of v. And here is where magic starts working and we are happy. Well, it's easy to see because if the degrees are equal, then the length of p tau of v is equal to the length of f of v, which is less than the length of tau. Hence, p tau of v is irreducible and it's equal to its reduct. So by the lemma p tau, we have f of v equals p tau of v. Now, I need one fundamental lemma, which I must say was the lemma which is the most technical and sort of hardest to prove in this result. The goal is to get degree of p tau equals degree of f, because then we know by the previous theorem that, p tau is equal to p tau of v is equal to f of v. So we want to get this degree of p tau equal degree of f. How shall we manage this? We will show this using this lemma, which gives a funny condition and then a contradiction. Assume that tau is, the length of tau is larger than the length of f of a. Then in case the degree of p tau is strictly less than k, we can find an L, which belongs to AB, one of the two letters AB, such that ret tau L of p tau of L is strictly larger than tau. I will give the idea of the proof of this lemma, fundamental lemma, in the next slide. Let's see first the consequence of the lemma. The consequence is that if tau is longer than f of a is equal to f of L, because A and L have the same length, so f of a and f of L, f is congruence preserving and having the same length is a congruence, have the same length. By the lemma p tau, f of L is equal to ret tau L of p tau of L. Now by the lemma which is just here, if tau is longer than f of a and degree p tau is less than k, ret tau L of p tau of L is larger than tau. So we have tau larger than f of L equals to this, strictly larger than tau, a contradiction. Hence, tau larger than the length of f of a implies equality of degrees and implies that for all nice v's, f of v is equal to p tau of v. So f of v is polynomial on all those v's, is partially polynomial on the v's that satisfy this condition. Now, next slide, I will give you an idea, very vague idea of the proof of this fundamental lemma. Well, you are not expected to read and check everything on this slide. Basically, the idea is that the proof is combinatorics on words in tau, words of tau words. I'll show you the simplest possible case, which is f of degree 2. So the length of f, assume the length of f of u is twice the length of u. So I have f is of degree 2. Assume tau is the shortest possible, a square b, a b square. Tau is of length 6. And assume degree of p tau is 1, strictly less than 2. Then p tau of x is one of these 5 polynomials, exactly one, believe me, please, of these 5 polynomials. And we check that in all of these 5 polynomials, one of p tau of a or p tau of p, one of the two, is tau irreducible and is of length 7, strictly larger than the length of tau. So this proves in this very small case the lemma, fundamental lemma. And now, hurrah, magic works. This is why we called it magic, because once we had found the taus, it was just the right congruence. As a consequence of the fundamental lemma, for any v, we can find a sufficiently large n such that if the length of tau is larger than n, then f of v is equal to p tau of v. You are going to say, well, you have a zillion polynomials p tau here, not a single one. But it so happens that if 2 polynomials are such that they coincide on a and b, then they coincide everywhere. And as all p taus are equal for tau large enough, their common value p satisfies f equals p. So any unary CP function is polynomial, and we have one for the unary case. The n-ary case is exactly similar, except computations are much heavier. It's an induction. We did the induction from 0 to 1, and the induction from n to n plus 1 is the same. So the Fremanoid on 2 generators, A, B star with concatenation, is affine complete. To conclude, well, just a word about 3 algebras. So let me say that the Fremanoid is an associative but non-commutative algebra, which is, so we have the whole picture for the Fremanoid. If it has 1 generator, it's not affine complete. And if it has more than 2 generators, it is affine complete, and it is an associative non-commutative affine complete algebra. Now, the 3 algebras are apparently more complicated because they are non-associative and non-commutative affine complete, but the proof is much simpler. It's similar but simpler because of the unique decomposition of trees. We have no overlapping problems. So any tree can play the role of tau, and the proof is easier. Some open problems. What happens if we have non-binary trees with labeled leaves, namely trees whose nodes are non-labeled, but nodes can be of arity, say 3, 7, 9, and the leaves are labeled by the elements of sigma. I suspect that the same holds, namely that these trees form an affine complete algebra. And the second problem, I have no idea whatsoever, would be to characterize affine complete binary 3 algebras. So thank you for your attention.